Sklearn Semi-Supervised. Description: Explain in detail. Semi-supervised learning in scikit-learn. Sklearn involves training machine learning models using a combination of labeled and unlabeled data. This approach leverages the valuable information present in unlabeled data to improve model performance, especially when labeled data is scarce. Inputs. Input 1. Explain in detail labeled data. This is the data with known class labels, which is essential for training the model. It provides the initial knowledge about the patterns and relationships in the data. Input 2. Explain in detail unlabeled data. This is the data without class labels. Semi-supervised learning utilizes this unlabeled data to infer and improve the model's understanding of the underlying data distribution. Outputs. Output 1. Explain in detail trained model. The semi-supervised learning algorithm outputs a trained model that is capable of making predictions on new, unseen data. Output 2. Explain in detail predictions on unlabeled data depending on the specific algorithm used. The trained model can generate predictions for the unlabeled data, thereby effectively labeling them. Steps. Step 1. Explain in detail initial training. The semi-supervised learning process starts with training the model on the labeled data. This provides the model with an initial understanding of the data. Step 2. Explain in detail incorporating unlabeled data. The unlabeled data is then introduced to the model. The algorithm utilizes this unlabeled data to refine the model's decision boundaries and improve its overall performance. Metrics. Metric 1. Explain in detail accuracy. This metric measures the proportion of correctly classified instances in the labeled data. It provides an indication of how well the model performs on the known data. Metric 2. Explain in detail F1 score. This metric measures the harmonic mean of precision and recall, providing a balanced evaluation of the model's performance. It is particularly useful when there is an imbalance in the class distribution. Visualization plots. Visualization plot 1. Explain in detail decision boundary plots. These plots visualize the decision boundaries learned by the model, highlighting how the model separates different classes in the feature space. They provide insights into the model's behavior and its ability to generalize to new data. Visualization plot 2. Explain in detail feature importance plots. These plots show the relative importance of different features in the model's decision-making process. They help identify which features are most informative and influential in determining the model's predictions. Fine-tune parameters. Parameter 1. Explain in detail regularization strength. This parameter controls the amount of regularization applied to the model. Regularization helps prevent overfitting by penalizing complex models. Parameter 2. Explain in detail number of iterations. This parameter determines the number of iterations the algorithm runs to refine the model's decision boundaries. A higher number of iterations can lead to better performance but may also increase training time. Uncertainty methods. Uncertainty method 1. Explain in detail entropy-based uncertainty. This method measures the uncertainty associated with each unlabeled instance based on its probability distribution over different classes. Instances with higher entropy are considered more uncertain and are given more weight during training. Uncertainty method 2. Explain in detail confidence-based uncertainty. This method assigns uncertainty based on the model's confidence in its predictions. Instances with lower confidence scores are considered more uncertain and are given more weight during training. Challenges and fixes. Challenge 1. Explain in detail data imbalance. If the unlabeled data contains a significantly different distribution of classes compared to the labeled data, it can lead to biased model learning. Sample use case that resulted in challenge 1 in a medical diagnosis scenario. If the labeled data mainly consist of healthy individuals and the unlabeled data contains a higher proportion of diseased individuals, the model may learn biased patterns and must classify healthy individuals. Fixes to challenge 1 oversampling or undersampling techniques can be applied to balance the class distribution in the unlabeled data. This ensures that the model learns from a more balanced representation of the data. Challenge 2. Explain in detail data contamination if the unlabeled data contains noisy or corrupted instances. It can negatively impact the model's performance. Sample use case that resulted in challenge 2 in a text classification task. If the unlabeled data contains spam messages or irrelevant content, it can confuse the model and lead to inaccurate predictions. Fixes to challenge 2. Data cleaning techniques can be employed to remove noisy or corrupted instances from the unlabeled data. This helps ensure that the model learns from clean and reliable data. Sklearn semi-supervised label propagation. Description. Explain in detail label propagation is a semi-supervised learning algorithm that uses graph-based methods to propagate labels from a small set of labeled data points to a larger set of unlabeled data points. It assumes that data points that are close to each other in the feature space are likely to have the same label. The algorithm works by constructing a graph where nodes represent data points and edges represent the similarity between them. The algorithm then propagates labels from the labeled nodes to the unlabeled nodes by iteratively updating the label probabilities of each node based on the labels of its neighbors. Inputs. Input 1. Explain in detail a matrix of shape and samples. N features containing the feature values for all data points. Input 2. Explain in detail y an array of shape and samples containing the labels for the labeled data points. Outputs. Output 1. Explain in detail labels an array of shape and samples containing the predicted labels for all data points, including the unlabeled ones. Output 2. Explain in detail the fitted label propagation object. Steps. Step 1. Explain in detail. Construct a graph where nodes represent data points and edges represent the similarity between them. This can be done using different similarity metrics, such as the Euclidean distance, the cosine similarity, or the k nearest neighbors. Step 2. Explain in detail. Propagate labels from the labeled nodes to the unlabeled nodes by iteratively updating the label probabilities of each node based on the labels of its neighbors. Metrics. Metric 1. Explain in detail accuracy, the proportion of correctly classified data points. Metric 2. Explain in detail F1 score, a measure of the harmonic mean of precision and recall. Visualization plots. Visualization plot 1. Explain in detail scatter plot of the data points with different colors representing the predicted labels. Visualization plot 2. Explain in detail confusion matrix, showing the number of correctly and incorrectly classified data points for each class. Fine-tune parameters. Parameter 1. Explain in detail gamma, the inverse of the bandwidth of the Gaussian kernel used to compute the similarity between data points. A higher value of gamma corresponds to a smaller bandwidth, resulting in a more localized similarity measure. Parameter 2. Explain in detail maxiter, the maximum number of iterations to run the label propagation algorithm. Uncertainty methods. Uncertainty method 1. Explain in detail confidence score. The confidence score for each data point is the probability of it belonging to the predicted label. This can be used to identify data points that are more uncertain about their label. Uncertainty method to explain in detail entropy. The entropy of the label probability distribution for each data point can be used as a measure of uncertainty. A higher entropy indicates that the data point is more uncertain about its label. Challenges and fixes. Challenge 1. Explain in detail overfitting to the labeled data. If the number of labeled data points is small, the algorithm may overfit to the labeled data and fail to generalize well to unseen data. Sample use case that resulted in challenge 1 in a binary classification task with 100 data points. Only 10 are labeled. The algorithm may overfit to these labeled points and fail to classify the remaining unlabeled points correctly. Fixes to challenge 1. Increase the number of labeled data points. Use regularization techniques, or use a different algorithm that is less prone to overfitting. Challenge 2. Explain in detail sensitivity to the choice of similarity metric. The performance of the algorithm can be sensitive to the choice of similarity metric used to construct the graph. Sample use case that resulted in challenge 2 in a dataset with a complex structure. A Euclidean distance metric may not capture the true similarity between data points. Using a different metric, such as the cosine similarity, may lead to better results. Fixes to challenge 2. Experiment with different similarity metrics and choose the one that performs best on the given dataset. sklearn semi-supervised label spreading. Description label spreading is a semi-supervised learning algorithm that propagates labels from labeled data points to unlabeled data points based on the similarity between them. It operates by constructing a graph where nodes represent data points and edges represent the similarity between them. The algorithm then iteratively spreads the labels of labeled points across the graph, influencing the labels of unlabeled points based on their connectedness. This method is particularly useful when dealing with datasets where only a small portion of the data is labeled. This is the feature matrix representing the data. It is a 2D array where each row corresponds to a data point and each column corresponds to a feature. This is the label vector, which provides the labels for the labeled data points. The length of this vector should match the number of labeled data points. Labels. This is the predicted labels for all data points, including both labeled and unlabeled data. This is a 1D array of the same length as the number of rows in X. Transdictive labels. This is a 1D array of the same length as the number of rows in X. However, it only contains the predicted labels for the unlabeled data points. The labeled data points will have their original labels unchanged. Construct the similarity graph. The algorithm begins by creating a graph where nodes represent data points and edges represent the similarity between them. The similarity between two data points is determined by a chosen distance metric, such as Euclidean distance or kernel function. Assign labels to labeled data points initially. The labeled data points are assigned their true labels. Unlabeled data points are assigned an initial label, typically based on a uniform distribution or a random assignment. Iterative label propagation. The algorithm iteratively updates the labels of unlabeled data points by propagating the labels of their neighbors. This process continues until convergence, meaning that the labels of unlabeled data points no longer change significantly. Accuracy. The accuracy of the model is evaluated by comparing the predicted labels of unlabeled data points to their true labels. This metric measures the percentage of correctly classified unlabeled data points. F1 score. The F1 score is a harmonic mean of precision and recall. providing a balanced measure of the model's performance. Decision boundary: a visualization showing the decision boundary separating different classes can be plotted based on the predicted labels. This allows for a visual understanding of how the model is classifying the data. Feature importance: a bar chart showing the importance of different features in making predictions can be useful for understanding which features are most influential. Alpha: this parameter controls the strength of the label propagation process. It represents the proportion of the label information to be used for propagation. Higher values of alpha imply stronger propagation, which can result in more confident predictions but also may overfit the labeled data. Gamma: this parameter controls the similarity between data points. A higher gamma value implies a more localized influence of neighboring data points on the label propagation, while a lower gamma allows for more global propagation. Confidence score: the algorithm can provide a confidence score for each predicted label, indicating the certainty of the prediction. This score can be used to identify uncertain predictions and potentially focus on those data points for further analysis or label correction. Entropy: the entropy of the predicted label distribution can be used as a measure of uncertainty. Data points with high entropy have a more uncertain label prediction. Challenge 1: the choice of the similarity metric can significantly affect the performance of a algorithm. If the chosen metric is not appropriate for the data, it can lead to incorrect label propagation and inaccurate predictions. Sample use case that resulted in challenge 1: using Euclidean distance as the similarity metric when the data has nonlinear relationships between features could lead to misclassifications. Consider using kernel functions, such as the Gaussian kernel, which can capture nonlinear relationships. Experiment with different similarity metrics to find the best one for the data. Challenge 2: the algorithm can be sensitive to noise in the labeled data. Incorrect labels can be propagated to other data points, leading to inaccurate predictions. Sample use case that resulted in challenge 2: a small number of mislabeled data points can significantly impact the overall performance of the model, especially when the proportion of labeled data is small. Fixes to challenge 2: use techniques for data cleaning and label correction to ensure the quality of the labeled data. Consider using robust versions of the label spreading algorithm that are more resistant to noise. sklearn, semi-supervised, self-training classifier. Description: the self-training classifier is a semi-supervised learning algorithm in scikit-learn that leverages a small amount of labeled data and a larger amount of unlabeled data to improve classification performance. It follows a two-step process. 1. Initial training: a base classifier is trained using the limited labeled data. 2. Iterative self-labeling: the trained model is then used to predict labels for the unlabeled data. The most confident predictions are then added to the labeled set, and the model is retrained. This process is repeated iteratively until convergence or a predefined number of iterations are reached. Inputs: Bayes estimator: the Bayes classifier, e.g., logistic regression, random forest classifier, to be used for training. This is a crucial input, as its performance directly impacts the overall efficacy of self-training classifier. Unlabeled data that will be used to expand the labeled set iteratively. This input is essential, as the algorithm relies on unlabeled data for self-labeling. Labeled data: this input is not directly provided to the self-training classifier constructor, but it is necessary to train the Bayes estimator initially. The labeled data typically comprises features and corresponding labels. Outputs. Fitted estimator after training. The self-training classifier provides a fitted estimator that can be used for making predictions on new data. The fitted estimator is a version of the base estimator, enhanced by incorporating information from the unlabeled data. Predicted labels. The self-training classifier can return the predicted labels for the unlabeled data, which may be helpful for analyzing the model's performance and understanding its labeling decisions. Steps. Initialize. The algorithm begins by initializing the base estimator with the labeled data. This step establishes a foundation for the self-training process. Iterative self-labeling. The self-training classifier enters a loop, where the fitted base estimator predicts labels for the unlabeled data. It then selects a subset of the most confidently predicted unlabeled instances and adds their predicted labels to the labeled dataset. The base estimator is then retrained with the expanded labeled data. This cycle repeats until a stopping condition is met, such as reaching a maximum number of iterations or achieving a desired level of performance. Metrics. Accuracy. The most common metric used to evaluate the performance of a self-training classifier is accuracy, which measures the percentage of correctly classified instances. However, it's important to note that accuracy may not be a reliable indicator of model performance when pay data is imbalanced. F1 score. This metric considers both precision and recall, providing a more balanced evaluation of the model's performance on imbalanced datasets. Recall. This metric focuses on the ability of the model to identify all positive instances. It is particularly relevant in applications where minimizing false negatives is crucial. Precision. This metric emphasizes the model's ability to correctly identify positive instances. It is relevant in situations where minimizing false positives is essential. Visualization plots. Learning curve. A learning curve plot can be used to visualize the model's performance, e.g., accuracy on both the labeled and unlabeled data as a function of the number of iterations. This can help identify if the model is overfitting or underfitting the data. Confusion matrix. A confusion matrix visually presents the model's performance by displaying pay number of correctly and incorrectly classified instances for each class. It can help identify specific weaknesses in the model's predictions. Fine-tune parameters. Maxiter. This parameter controls the maximum number of self-training iterations. It can be adjusted to balance the trade-off between computational cost and the potential for further improvement in the model's performance. Threshold. This parameter specifies the minimum confidence score required for a predicted label to be considered for inclusion in the labeled dataset during self-training. This threshold plays a crucial role in controlling the quality of the pseudo-labeled data used to improve the model. K-best. This parameter determines the number of unlabeled instances with the highest confidence scores to be added to the labeled set during each iteration. A higher value may lead to faster convergence but may also introduce noise if the model is making inaccurate predictions. Sampling strategy. This parameter allows you to control how the unlabeled instances are sampled during self-training. For example, you can choose to sample a fixed proportion of unlabeled instances or use a more sophisticated sampling strategy like random sampling or sampling based on confidence scores. Uncertainty methods. Confidence score. Self-training classifier typically relies on the confidence score of pay predictions made by the base estimator for selecting the most confident unlabeled instances. Instances with high confidence scores are more likely to have been correctly classified by pay model and are therefore more likely to be beneficial for self-training. Entropy. In some cases, Entropy-based methods may be used to estimate uncertainty. The entropy of a prediction reflects the diversity of possible labels for a given instance. Instances with low entropy, indicating less uncertainty, are considered more confidently classified and thus more suitable for self-labeling. Challenges and fixes. Challenge 1. Initial model bias. If the base classifier is trained on a limited and potentially biased labeled dataset, it can lead to the propagation of this bias to the unlabeled data during self-training. This can result in the model making inaccurate predictions and ultimately leading to poor performance. Sample use case. Imagine training a classifier on a dataset with a strong bias towards a specific class, resulting in the model's inability to identify instances from other classes. This bias might then be reflected in the unlabeled data, further reinforcing the initial bias. Fixes. Pre-processing prior to training. Carefully consider pre-processing techniques like data augmentation or oversampling to mitigate class imbalance and reduce bias in the labeled data. Model selection. Choose a base classifier that is less prone to bias, like a robust ensemble method or a regularized model. Early stopping. Implement early stopping during self-training to prevent the model from overfitting to the initial bias. Data validation after training. Conduct thorough data validation to identify and address any potential biases in the models. Predictions. Challenge 2. Label noise. As the self-training process involves adding predicted labels to the training set, any errors made by the model during self-labeling can introduce noise into the data. This label noise can further degrade the performance of the model over time. Sample use case during self-training. If the model incorrectly labels an unlabeled instance, this incorrect label becomes part of the training set in subsequent iterations, potentially leading to a cascade of errors. Fixes. Threshold tuning. Adjust the threshold parameter to increase the confidence level required for adding a predicted label to the training set. This reduces the chance of adding noisy labels. Ensemble methods. Utilize ensemble methods that combine predictions from multiple models to reduce the impact of individual prediction errors and improve robustness to label noise. Confidence-based sampling. Prioritize adding unlabeled instances with high confidence scores to the training set, reducing the likelihood of introducing noisy labels. Data cleaning. Periodically evaluate and clean the labeled dataset for potential errors. Removing noisy labels.